Hello, and welcome to this presentation on decentralized wastewater systems, also known as on-site systems or septic systems. This presentation is one in a series of presentations on the operation, maintenance, and management of water and wastewater utilities, designed for the managers and operators of small utilities serving Native American tribes and Alaskan Native villages. Many of the experiences gained through others who have attended these trainings are part of the discussion that we'll have here today. One thing that we've learned from the presentations in different parts of the country is that each and every tribe that we talk with utilizes decentralized or on-site systems to manage wastewater for at least a portion of their community. All of them have issues that they are facing regarding the management and operation of these systems that we'll touch on in the presentation today. Conventional on-site systems or decentralized systems utilize three major components to manage wastewater. The first is the septic tank, the second is the distribution box, and the third is the leaching area. As shown in this graphic, as effluent leaves the home or business, it flows to the septic tank, where solids are settled out of the liquid. The liquid then flows to a distribution box, which evenly disperses the effluent out to a leaching field or other dispersal field, where the effluent then filters down into the ground. We'll go through each of these components as we move forward within the presentation and give you more detail on all of them. A decentralized system or an on-site system can be used for a single lot or for a clustered wastewater system as shown on this slide. In this case, a series of 8 homes are connected by a small sewer line which runs down the road. Effluent flows by gravity to one centralized septic system that contains the septic tank, the distribution box, and the dispersal facility. This can be done if the soils on one or more of the lots are poor or are inadequate for an on-site septic system, or to move effluent from an area that may be environmentally sensitive and have the discharge take place further from that environmentally sensitive area. On the last slide, we talked for a moment about environmentally sensitive areas. One way that septic systems are managed to protect these are to apply setbacks. A setback is a minimum distance that a septic system, or one of its components, can be located from a surface water, wetland, stream, local private well, steep slopes, or other environmental factor that plays into the design of the facility. These setback distances can vary from location to location across the country. They're based on local conditions and on local health regulations promulgated either by the tribe or local community, or sometimes at the state level. As you think about this, what are appropriate setbacks to some of these environmentally sensitive areas? For instance, what is an appropriate setback between a septic tank and a surface water? How about a septic tank and a water supply line, or a septic tank and a property line? This table shows 2 examples of setback distances used to regulate the location of septic systems in different parts of the country. The U.S. Public Health Service has a recommended distance for setbacks to dwellings, property lines, and other features. Similarly, Contra Costa County in California has setback distances. Many of them are similar, although you'll see a couple of differences. If you look at the setback distance between a septic tank and a surface water, in both situations there must be a 50-foot distance between the septic tank itself and the surface water. The distance to a water supply line that's under pressure in both situations is 10 feet, and the distance to a property line is 10 feet under the U.S. Public Health Service criteria and 5 feet in Contra Costa County. You'll notice there are some differences in the length of these setback distances. It is more important to be some distance from the surface water, so the effluent, if it leaches out of the septic tank or is leaching from the leach field itself, has some time to be filtered and somewhat treated before it discharges to the surface water. The distance to a property line doesn't have to be that far, and the main reason for this is the property line setback is to make sure the construction of the system doesn't harm the abutting property. The trees and vegetation shouldn't be disturbed on one property when a septic system is being installed on the adjacent property. So let's start looking at the 3 main components of the septic system. The first is the septic tank, as shown on the picture here. Effluent from the home or from a business comes in through the inlet pipe. The inlet pipe has a T at the end of it, so the effluent itself is discharged down into the septic tank. In the tank, the effluent separates. Solids that will sink filter their way to the bottom to become part of the sludge layer. Other solids, such as paper, will float to the surface and become part of the scum layer. The inlet tee and outlet tee are designed in part to make sure that the scum does not move from the septic tank either back into the house or out to the distribution box and then to the leach field. The outlet tee takes the clearer water, not necessarily clean water, but cleaner water, where the solids have been filtered out, and runs them from the middle of the tank up the outlet tee and out to the distribution box. As you can see here, as well, there's a cover. Typically there are two, one near the inlet pipe and one near the outlet pipe, so both of these can be accessed and maintained if necessary. Septic tanks can be built from a variety of different materials. Often they are constructed out of precast concrete, typically in two parts with the bottom connected to the top as the system is being constructed in the field. They can also be built out of fiberglass or polyethylene plastic, or in some cases steel, although metal tanks tend to corrode when they sit in the soil for some time, allowing effluent to escape the tank. If your house is connected to an on-site system using a septic tank, there are two things you need to avoid. For starters, it's not good to have a garbage disposal in your kitchen sink connected to a plumbing system that drains to a septic tank. The increased number of solids discharged through the sink can affect the functioning of the system and can overload the septic tank and eventually lead to the plugging of the leach field itself. If a garbage grinder or garbage disposal is used within the home, the size of the leach field likely needs to be expanded. Many states and local communities have regulatory programs that require a larger leaching field and sometimes a larger septic tank to accommodate the increased solids from the garbage disposal. You also have to consider toxic substances which can kill the bacteria in the septic tank and harm the treatment that does take place within the system. Things such as strong medications, photochemicals, petroleum-based products or solvents, paint thinners, insecticides or pesticides are things that should not be poured down the drain. Septic tanks need to be pumped on a regular basis to remove the solids before they accumulate to a level where they can make it through the outlet pipe and out to the leaching facility. For a typical home, a septic tank should be pumped once every 2 to 3 years. If the home has higher occupancy, or if the septic system is connected to a business with a higher water flow or a higher pollutant load, then pumping should be done on a more regular basis. You can check whether or not the system needs to be pumped by measuring the thickness of the sludge in the scum layer within the septic tank. This can be done by opening one of the access hatches to the septic tank and measuring the thickness of the sludge layer on the bottom and the scum layer at the surface. Often this is done with a transparent plastic pipe that's lowered down into the septic tank. It has a check valve at the bottom, and as you pull it up, it shows you a profile of the layer of sludge and the layer of scum within the tank. It functions very similarly as a straw does when you stick it in a glass of juice or a glass of soda and put your thumb over the top and pull it out. It pulls out the liquid that had been collected within the straw. This PVC pipe can do the same thing and give you a fairly accurate reading of the thickness of the sludge at the bottom and the thickness of the scum at the top of the septic tank. By measuring the sludge and the scum layer and tracking their accumulation over time, you can determine when the optimum time is to pump the septic tank. The second major component of a septic system is the distribution box, and this is used to accept the effluent from the septic tank and disperse it evenly across the leaching field or leaching trenches. The idea here is to not have the effluent come from the septic tank and discharge all in one location within your dispersal facility, but to take that effluent and spread it evenly around the disposal facility. This maximizes the life of the system and makes sure that one area is not overloaded while others are not receiving any effluent. Often this is done with one pipe from the septic tank coming into the distribution box and 3 or 4 or more outlet pipes heading from the distribution box out to the leaching facility. The distribution box is constructed to be as level as possible, but as are shown on the graphics on this slide, a speed leveler can be used to make sure that the outlet to each pipe heading from the distribution box out to the leaching facility is equally level. The speed levelers are a cap that goes on the end of the PVC pipe, and you can turn the openings such that they're all even with each other and water is flowing equally into each of the pipes that head to the dispersal bed or leaching facility. The third component of the septic system is the effluent dispersal field or leaching facility. The keys to making sure that this component of the septic system works well is the location in which it sits on the property and the relationship of it to the soils underneath it and the environmental receptors that are around it. We want to make sure that the soils are adequate to allow the effluent to percolate down through the ground as opposed to bubble up to the ground surface. And that's a function of the permeability of the soil in the surrounding area. The types of soils will also play a role in the reduction of solids and bacteria that are in the effluent and will help to treat them before they make it down to groundwater. As the wastewater is passing through the soil, it receives treatment through filtration. Particles such as bacteria will be filtered out and trapped in the soils and won't move very far, perhaps less than 5 to 10 feet from the dispersal facility. Phosphorus, a nutrient that can affect freshwaters such as lakes and ponds, is typically absorbed or attached to the sediments near the leaching facility and also won't travel very far. A proper setback from a septic system to surface water is designed in part to minimize phosphorus impacts. There are also biochemical reactions that can take place, primarily to transform organic nitrogen into ammonia and nitrate nitrogen, and remove some of that before it enters groundwater. So the siting of the on-site septic system is important and needs to be looked at carefully to make sure that it is in an area that won't create a public health threat or an environmental problem. There are a series of factors that the septic system designer needs to consider in order to determine if the site is suitable for effluent dispersal. Can you think of what some of these factors may be? We're going to list 5 of them on the next slide. One of the first one that needs to be looked at is the depth to high groundwater. This is done by digging a hole in the ground, or a test pit, and measuring the depth to water if in fact you encounter water. You want to make sure you have a minimum of perhaps 4 to 5 feet of dry soil below the bottom of the leaching bed in order for it to function properly. If there's less than that, there's a potential for groundwater and effluent to back up through the system during high water periods and create a failure of the whole system. When you're looking at the depth to water, you want to make sure you're looking at the maximum water level. Groundwater levels can fluctuate significantly on a seasonal basis, and this varies from place to place within the country. Depth to high groundwater can be determined by conducting the measurements and digging your test pit during the high water period of the year, typically in the spring months of April or May. And again, that will vary in different locations around the country. It can also be determined by looking at the soil profile itself, and a qualified soil scientist is capable of reading that soil profile and estimating where maximum high groundwater might be by looking at the staining or soil models within the soil profile. By measuring the height of these soil models in the soil profile in the test pit, it's possible to estimate the depth to maximum high groundwater. As you're evaluating your site, you also want to look at the distance to surface waters or wetlands, and make sure that you can comply with the setbacks that you need to meet. As we mentioned earlier in this presentation, the distance for a septic system dispersal facility to a surface water or wetland will often be 50 feet, as it is on the table we showed you earlier. In some communities, that setback is increased to 100 feet and sometimes beyond, in order to minimize the impacts of the effluent discharge from the septic system out to the surface water. Steep slopes need to be identified. If you have wastewater percolating down into the ground and it's on the edge of a hill, it may break out at the land surface and become available for contact with humans. You also want to make sure you know the distances to property lines. You don't have to be too far from the property line to build a septic system, but you need to know where those are, and they need to be properly surveyed by a professional land surveyor in order to make sure you've got the proper setbacks. And then finally, and perhaps most importantly, the distance from the septic system to a drinking water well needs to be identified. You don't want to have short-circuiting, where the septic system is too close to a well, and the water that's pumped from that well for drinking water purposes contains effluent that's been discharged from the septic system. Most communities require a minimum of a 100-foot setback between a well and a septic system to avoid contamination. We talked about test pits on the last slide. The picture on the left here shows a sample test pit that's been dug 5 or 6 feet down into the ground, and you can see the groundwater that's percolated into the hole. This is used to measure the depth to maximum groundwater within the test pit. In addition, once a test pit is dug, a percolation test is run to measure the infiltration rate for effluent that's moving through the soils. This is done as shown in the photo on the right side of this slide, where a smaller hole is dug within the bottom of the test pit. This hole is filled continually with water until it saturates, and then the rate of infiltration, or the rate at which the water soaks down into the ground, is measured. That rate of fall, or that infiltration rate, is then used to estimate the permeability of the soils, and is then used to size the extent of the leaching facility itself. In very tight soils, the percolation rate can be quite low, such that the water in the test pit is falling at a rate of 1 inch over 30 to 40 minutes. In very permeable soils, such as a coarse sand, the infiltration rate may be faster, and is often measured in these soils at a rate of 2 minutes per 1 inch of fall. Conventional on-site systems use a variety of different infiltration systems for dispersing effluent. We'll show you a number of these, including seepage beds, leaching trenches, and absorption mounds. Seepage beds are one form of effluent dispersal facility. They're typically wider than 3 feet and less than 100 feet long, and are used to dispose of primary treated wastewater. As this slide shows, a seepage bed is built with effluent pipes running through washed gravel, which is then covered with a filter fabric, such that when the septic disposal field is covered with the topsoil that you see on the sides of the bed, the fine materials in this topsoil won't work their way down into the gravel where the effluent is being discharged. Similar to a seepage bed is a leaching trench, and leaching trenches are used typically for larger facilities where you have a series of trenches, one next to the other. They're typically 1 to 2 feet wide, and a space is left in between them that is the same width. This space can function as a reserve area in the future. If for some reason the area of the trenches themselves become clogged, it's possible to rebuild the system by shifting everything over to use the areas in between the existing trenches. Each trench is built with a PVC pipe that's perforated, so the effluent leaving the distribution box flows into the trench and exits through the holes in the perforated pipe. The pipe is surrounded by washed gravel that's very permeable, and if a larger flow of effluent is coming in, it can actually be stored in the pore spaces around the gravel while it seeps into the ground below. The gravel itself is covered with a filter fabric, both below it and above it, such that the soils around the trench don't become clogged with any finer material that may exist in the naturally occurring soils. As you can see at the back end of the slide, there's a vent pipe that's installed to make sure that air can move in and out of the trenches on a regular basis. In larger systems, leaching trenches can be pressure dosed, where the effluent is forced into the trench under pressure from an effluent pump station. This picture shows an example of a pressure dose system that's being tested after final construction, before the last portion of the leach field is backfilled with the native material above it. You see a series of small pipes with water flowing out of them. This is water flowing under pressure as part of a clear water test to prove that the pressure dosing system is working. This is the far end of the leaching trench from where the water enters it, and it's showing that water is flowing under pressure at the far end, which also implies that it's flowing out into the trench along its whole length. As you see here, there's a series of larger PVC pipes next to the pressure dosing lines. These are air vents that are installed separately from the pressure dose lines. The pressure dose line is typically a very small PVC pipe with a small aperture placed at regular intervals along it to make sure that the water can be forced from where it begins at the beginning of the leaching trench all the way to the far end. At the back end here you can also see a cleanout where the pipe bends with an elbow up towards the land surface, such that if there is ever a clog within the pressure dosing line, you can get a snake or other piece of equipment within there to clean out the clog. The final type of absorption system or dispersal system we'll talk about is an absorption mound. This can be built as a seepage bed or as a leaching trench, but is built such that a portion of it lies above the naturally occurring ground surface. This is done in areas where the depth to water may be quite shallow, and it's needed to create the necessary separation between groundwater and the leaching bed. As you can see here, the ground is mounded up to cover the dispersal facility itself, and then is backfilled with topsoil and planted with vegetation. Typically, you're only planting grass over a system like this because you don't want to grow vegetation whose roots would impact the dispersal of the effluent. The material that's used to create the mound is typically good, clean sand to allow the effluent to percolate down into the ground. In addition, the topsoil at the natural ground level needs to be removed and replaced with clean sand, so there's no breakout of the effluent at the ground surface. So we've talked about the traditional septic system that includes the septic tank, the distribution box, and some sort of dispersal field, including the various examples we've just gone through. It is also important to note that there are a variety of different alternative treatment system components that can be added to a septic system to improve the quality of the water that's discharged through the leach field and down into the ground underneath. This is often done to help protect drinking water wells, coastal waters, or freshwater lakes or ponds from the effluent that's discharged from the septic system. The goals or the purposes of using an alternative septic system typically revolve around the need to remove or reduce the level of nitrogen that's discharged through the septic system. This can be done to protect drinking water wells and also done to protect coastal waters where excess levels of nitrogen can affect the quality of the coastal embayment, harbor, or bay. Alternative systems are often used to reduce the level of biological oxygen demand to result in a slightly cleaner effluent, and also to reduce the level of total suspended solids. Here is one example of an alternative septic system component, a recirculating or gravel sand filter, and the processes that take place within this sand filter are very similar to many of the proprietary septic systems that are available on the market today. So we'll run through how the system works. Effluent from the house enters the septic tank, and from here the solids are separated and the clearer effluent from the center of the tank, as we discussed earlier, is sent by gravity to a pump chamber. The pump chamber sends the effluent up to a sand filter and discharges it across the top of the filter. Oxygen is present within the sand filter, and as the water is filtering through the filter, the suspended solids are trapped, and bacteria that utilize oxygen transform the organic nitrogen within the organic wastes of the wastewater effluent to nitrate nitrogen, the oxidized form of nitrogen. As the effluent moves through the sand filter, a portion of the ammonia within the effluent is also volatilized and sent up into the atmosphere. When the effluent filters through the filter, at the bottom of the filter, a portion of that water, or semi-treated effluent, is recirculated back to the septic tank. The septic tank exists in an anoxic environment, meaning there is little to no oxygen present within the organic wastes within the tank. When the nitrate nitrogen from the sand filter is sent back into this environment, there are bacteria present that will convert the nitrate to nitrogen gas. And this nitrogen gas then moves back up into the atmosphere, where 70% of the air we breathe is nitrogen gas, basically removing the nitrogen from the effluent. The other portion of the effluent that filters through the sand filter is sent out to a leach field or dispersal facility. All in all, with this recirculating process that takes place, you can get about a 50% removal of overall nitrogen from the system, as well as significant removal of biological oxygen demand and total suspended solids. As you think about septic system management, who is it within your tribal community that takes care of on-site septic systems? In the presentations we've done in different parts of the country, we've seen a variety of different models in terms of who is managing on-site septic systems. In some cases, it's the homeowner that's responsible for taking care of their own system. For other tribes, the wastewater treatment plant operators may be tasked to also take care of the on-site septic systems for houses that aren't connected to the centralized facility. In this case, they do occasional septic system inspections and manage the pumping or the fixing of the systems on a needed basis. The first part of managing an on-site septic system is knowing what you have, and that involves a system inspection. You need to inspect the system components to make sure that the overall system is functioning properly. This is typically done by a qualified inspector, and they investigate the type and the size of the system. They look back at maintenance records to see how often the system has been pumped or whether it has been repaired recently. They evaluate whether it's located properly relative to the setbacks needed to surface waters or drinking water wells. They inspect how the building sewer looks and how that connects out to the septic tank. They look at the T's, the inlet and outlet T in the septic tank to ensure they're functioning properly. They make sure that the distribution box is level and water is flowing evenly out to the leaching area. And they inspect the leaching area if possible to make sure there's been no backup or clog within that system. These inspections are done for any type of septic system and are often used to identify systems that either are malfunctioning or don't meet the current design codes used by the tribal community for managing their on-site wastewater. It's a good way of knowing where the systems are located, how they're operating, and which ones need to be upgraded or improved to meet current requirements. EPA has developed a series of septic system management recommendations, or management models, that can be used to highlight some of the different techniques that tribes and other communities can use to manage on-site septic systems. There are 5 models that are shown here on this slide, and there's a website to obtain this technical document for further review if you're interested. These 5 management models begin with the most simplest one, involving homeowner awareness, and move up the scale of complexity and cost up to the point where the community itself may own and operate the septic systems that are located on individual people's properties. Starting at the beginning of these management models, the homeowner awareness model basically involves the local community providing outreach and educational materials to homeowners that are responsible for managing the septic systems on their own. As we move up in complexity, there can be requirements where homeowners have a maintenance contract where they hire out to someone who's qualified to manage their on-site system. This can be very helpful if there are alternative components connected to the system that provide increased treatment, like some of the systems we discussed previously. The regulatory authority can also require operating permits, or can also take on the operation and maintenance of the septic system themselves and bill the homeowner for the costs of doing this operation and maintenance. In this manner, especially for more complex systems, it's possible to make sure that they're functioning properly and they're meeting the treatment levels that are required for the system. And as I mentioned a little bit earlier, the regulatory authority or the tribal community can actually own the on-site septic systems and therefore be responsible for their ongoing operation and maintenance, as well as their upgrade and replacement over time. The website where you can find more information on these different management models is shown here on the slide. This concludes our presentation on decentralized or on-site wastewater systems. We've discussed the various components that are part of an on-site septic system, including the septic tank, the distribution box, and the leaching facilities or drain field. We've talked about the environmental setting where septic systems are installed and discussed some of the various setbacks that should be maintained, such that a system is protective of public health and the environment. And we've given a brief overview of the different types of alternative septic systems used to increase the level of treatment from an on-site system. To learn more about on-site systems, I encourage you to investigate the web links that are shown on this slide, which provide additional materials from EPA and others on this topic.